Let's put these ideas for trapezoid and Simpson's rule into what I'll call integration routines for evaluatable functions. Here we're going to assume that the function to be integrated is known and it can be evaluated at as many points as desired. It's not just that function data xy pairs are given. The function f exists as a computer program and can be evaluated at any location desired by the integration algorithm. Let's see how we can use that. So you first pick a method, trapezoid or Simpsons, and set some sort of stopping tolerance for accuracy. Then pick k, the initial number of subdivisions, and iterate as follows. Apply the composite method using k divisions, and then also apply the composite method using 2k divisions. If the answers are within tal of one another, in other words, when you doubled the number of divisions, the result from the integration essentially came back the same, then stop and return the 2k division answer. If the answers are not within tal, then increase your number of subdivisions and repeat this whole process. So you keep increasing until the result from a composite method at k divisions is approximately equal to the result using the same composite method and twice the number of divisions. Now, there's a couple caveats here. With this limited analysis where the iteration stops simply because the k division and 2k division results are nearly the same, we can't guarantee that the computed answer is accurate to any specific precision. But it's a good heuristic stopping criteria, and for the most part, only functions which have been specifically constructed to fool this stopping criteria will get very erroneous answers. The other caveat is if there are regions where the function changes rapidly, then the final number of subdivisions may end up having to be very high in order to get this convergence. But what that also means is for that same function in regions where it was not changing rapidly, there's probably many unnecessary function evaluations. So what we'd like to do is deal with that in what's called an adaptive step size manner. Let's see how that works. The strategy is to somehow only use small h, we'll call that the step size, where the convergence demands it. Here's a really neat recursive implementation. Right here is just pseudocode. So there's some function that returns the integral from a to b with accuracy tal. And accuracy is in the way we described. The k subdivision and 2k subdivision results are nearly the same. So first compute the answer using one subdivision. We'll call that answer I1. And then compute the answer using two subdivisions. Call that answer I2. If they are within tolerance of one another, then stop and return the I2 answer, as it's likely more accurate. If they're far apart, then split the original interval, which is from a to b, into two intervals. So m is the midpoint, a plus b over 2. Then recursively call this function, integrating from a to m, call that I left, and insist on a tolerance which is the original tolerance divided by 2. Also integrate the right side from m to b, again with an accuracy of tal over 2, and then simply add those two results for the integral. These two lines are a recursive call to this program. Integrate the function over a smaller interval with a tighter accuracy. Let's do this for a trapezoid. Here's a naive version. So the function handle is passed in as well as a, b, and tal, and the integral is passed back. Evaluate the function at the left endpoint. Evaluate the function at the right endpoint. That would allow us to do the one subdivision trapezoid. We also need to do the two subdivision trapezoid as well. So determine the midpoint and evaluate the function there. Finally, define a variable h and then compute the integral based on one subdivision. Well, that's easy. 1/2 times fa plus fb times h. Also compute the integral based on two subdivisions. And there we see the 1, 2, 1 pattern and h over 4. Now you may be wondering, why does it say h over 4? All the formulas had h over 2. That's correct. Remember though that the h for two subdivisions is 1/2 of b minus a, and here h has been defined as b minus a. So I need to take 1/2 of h to get the actual h, and then 1/2 of that for the formula. Now we simply follow the pseudocode. If the two integrals are close, then return the second one. Otherwise, call this function recursively. Integrate from a to m with an accuracy requirement of tal over 2, and integrate from m to b with an accuracy requirement of tal over 2, and add those two results, and that will be the answer. Now this is a little bit naive. Let's see why. Let's track where the function gets evaluated. Call this, with 4 input arguments, a function a and b and tal. Within the first 4 lines, the function has been evaluated at a, b, and m, as shown there. Suppose that this is not adequate for the convergence. The integral 1 and integral 2 are far apart, so the function gets called recursively. So on the first recursive call, the endpoints are now a and m. This AR trap gets executed again, and the function f gets evaluated at the left endpoint, which is a, the right endpoint, which is m, and the middle, which is shown there. And maybe that is adequate enough for convergence, so that side is done. Next, it moves to the second call to AR trap, where the limits are m and b. In that subsequent call, the function is evaluated at m, b, and the midpoint. Let's suppose that that isn't adequate enough for convergence, so 2 more recursive calls have to occur. In the next call, the function gets evaluated at the 2 endpoints and the midpoint. Assume that's adequate for convergence, so the other call gets called, and it also gets evaluated at the 2 endpoints and the midpoint. And let's suppose that's adequate enough for convergence. At this point, the function would exit, but look and see what's happened. We've actually done 15 function calls, but only in 7 different locations. So there's quite a bit of waste, almost a factor of 2 extra function calls that did not have to be repeated. The function got evaluated twice at a, 4 times at m, 3 times at b, and 3 times at the midpoint between m and b. All unnecessary if we could have tracked that value somehow better. We'll figure out how to get around all these extra function calls momentarily, but let's not lose sight of what the idea behind the adaptive step size was and whether or not it worked. So for the time being, forget about all these multiple function calls. Let's just track where has the function being integrated been evaluated. It's been evaluated at a, at the midpoint between a and m, at m, and then at 3 intermediate points between m and b, and at b. Notice that the density of these function evaluations is different along the line, and that's the point of the adaptive step size. Now let's see how to fix it. Okay, so here's the improved version. First thing to notice is that rather than 4 input arguments, there are 6 input arguments. But the first thing checks to see whether or not it was called with 4. 4 is the normal manner in which a user will call this, passing in a function handle, the 2 limits of integration, and the tolerance. If that's how it is called, then the first thing it must do is evaluate the function fh at the 2 endpoints, a and b. Notice if nargan is equal to 6, this will not happen, and it's assumed that fa and fb are being passed in. The function value at a and the function value at b are somehow known and have been passed in. Next, the midpoint is calculated, and the function is evaluated at the midpoint. And the 1 and 2 subdivision integrals are computed, I1 and I2. The tolerance is checked. If it passes, we're done. If not, the recursive call occurs. And these are a little bit different. Let's look at the first 4 arguments to make sure this makes sense. I left is the integral of fh from a to m with an accuracy requirement of tal over 2. That's the same. The thing is we already know what the function value is at these 2 endpoints, fa and fm, because we have them. Either fa was passed in or it was computed in this particular instance of the function, but in any case, it's now known. fm was computed in this instance of the function, and it is known. Let's pass those on to the next call so that there's no need for the next call to compute f of a or f of m. Similarly, for the other recursive call, the first four arguments are what they used to be. We want to integrate fh from m to b with an accuracy requirement of tau over 2. But we already know the value of f at m, and we already know the value of f at b. So let's pass those to this call, and then finally finish by adding those two up. Let's take a pictorial view of what happens here. Well, the first time through, the user calls it with four arguments, fh, a, b, and tau. There's no passing in of fa and fb. So the function gets evaluated at a and b in line 3, and finally at m in the 5th line. As before, let's imagine that's not suitable for convergence, so we have to make this first recursive call to compute I left, integrating from a to m. But now, fa and fm, the left and right endpoints, are passed in. So in this subsequent call, there are 6 input arguments, and the function is not evaluated at a or at m. It's only evaluated at the midpoint. Now, like before, let's assume that's adequate for convergence. So now the trapezoidal routine moves to the other interval, I right. And because that is passed with 6 input arguments, only the midpoint function evaluation occurs. Let's assume that's not adequate for convergence. So another I left and I right call are generated. The I left call passes in the extra 2 arguments. Therefore, no extra function evaluations occur. Only the midpoint is calculated. And ditto for the I right call. In the end here, only 7 function evaluations are used. All the other ones are reused by properly passing them in through the extra 5th and 6th input argument. Adaptive Simpsons works the same way. Let's write it in the non-naive case with the extra input arguments. 4 input arguments is the normal way to call it for a user: function handle, a, b, and tolerance. But there's also a possibility of 7 input arguments: the function value at a, the function value at the midpoint between a and b, and the function value at b. Initially, m is set to a plus b over 2. And then if the number of input arguments is 4, a typical user call, well, evaluate the function to be integrated at the 3 locations: the left endpoint, the midpoint, and the right endpoint. H is b minus a, and form the integral using the 1 and 2 subdivision Simpsons rule. The 1 subdivision Simpson rule has the 1-4-1 pattern with h over 6. Now for the 2 subdivision, we need to make 2 more function evaluations at the midpoint between a and m, and at the midpoint between m and b. Call those m1 and m2. Make those function evaluations, and then the formula for the 2 subdivision. Notice the weighting pattern, 1, 4, 2, 4, 1. And remember, the reason the h over 12 is the same reason we had h over 4 in the 2 subdivision trapezoid line 2 slides ago. Now, if the tolerances are satisfied, return I2. Otherwise, make recursive calls. To the left, let's look at the first 4 arguments. Integrate fh from a to m with an accuracy requirement of tau over 2. However, since the value of the function is known at the left endpoint of this interval, the middle of this interval, and the right point of this interval, pass them in. Those are fa, fm1, and fm. Similarly, do the integral on the right. That's the integral of fh from m to b with an accuracy requirement of tau over 2. But again, the function value at the left endpoint, the middle, and the right endpoint are already known, so pass them in so that the recursive call has to do less function evaluations. And then finally finish. What does this look like? Suppose the user makes a call with only 4 input arguments. Well then, the nargan equal 4 line runs, evaluating the function at a, m, and b. And the fm1 and fm2 lines run, evaluating the function at m1 and m2. 5 function calls have occurred before the recursive calls even start. Now, if the recursive calls start, let's look and see what happens in the I left call. In the I left call, 7 input arguments are used. Therefore, in that subsequent function instance, only the midpoints need to be evaluated. The conditional for the nargan equal 4 line is not executed. The picture of what happens is that only the 2 solid lines get evaluated in that recursive call. And this type of process happens for all the subsequent recursive calls. only the new midpoints are evaluated. Let's try some of these in MATLAB. Here we are in MATLAB. I'm looking at the adaptive recursive Simpsons with the 7 arguments. User calls it with 4 arguments, the function handle, a, b, and the tall. It's laid out exactly the same as in the slides. There's only one additional thing I've done here, is I also return the points at which all the evaluations took place, so that we can look at that and see that it is distributed unevenly based roughly on how quickly the function that's being integrated is changing. So I had to make some changes to return that, but that's done. And now let's go to the example that I want to run. And we'll do it on the function 2 plus sine of x squared. So because it's sine of x squared, the frequency gets greater as x gets larger. We'll go from 0 to 5 for the range of integration. We'll set the tolerance initially to be 0.05. We'll integrate it using our method. We'll also integrate it using the MATLAB built-in integral function, which works very much under the same principles. And we'll see the difference between the two values that we both obtain. Then we'll take the interval and we'll compute on a very dense grid what the function looks like. We'll also look and see what the function looks like on the sample points where the integration took place. And we'll plot that. A smooth graph for the function, and then red circles where the adaptive recursive Simpson actually made function evaluations. For the title, we'll give the value of the integral as returned by our algorithm, as well as the difference between the MATLAB function integral and our result. On the lower plot, we'll plot a histogram. You may not have learned about histograms, but we'll cover them in the statistics lecture. What we'll do is we'll take the points where the function evaluations actually took place, and we'll divide them into 15 buckets spread evenly from 0 to 5. So these buckets are each of length 1/3, and we'll count how many function evaluations took place in the interval 0 to 1/3, how many took place in the interval 1/3 to 2/3, 2/3 to 1, all the way up to 4 2/3 to 5. So that's what the 15 buckets are. And this will show us the different counts that we obtain. Let's run this. So what we see is that we obtain an integral of 10.5282. The difference between our return value and MATLAB's is about 2 10,000ths. The red dots are the samples of where our adaptive recursive Simpson algorithm ended up evaluating the function. It's hard to see the density from this point of view, but here show the number of points in each bucket. So from 0 to 1/3, there are 3 points. It's those 3. From 1/3 to 2/3, there are 2 points, and so on. There are 2 points in many buckets. Then it gets a little steeper, and there's up to 5 points in a bucket. And it holds steady at about 4. And then as the function rapidly varies more and more, the adaptive algorithm has put more and more points in each bucket. 9 points in this last 1/3 interval. Let's try the tolerance a little lower, in other words, tighter, 0.005. We'll just run this again. A couple things to notice. The difference between our value and MATLAB's value is now about 7e minus 7. Our points are denser than they used to be, but they still follow this trend of increasing density as the function rate of variation increases. Let's try another one, 0.005. Denser again, same trend of increasing density as x increases, where the function varies more rapidly. The difference between our computed value and MATLAB's is about 4 times 10 to the minus 6, a little bigger than in the past. Remember how our stopping criteria is met. It's when the 1 subdivision approximation is close to the 2 subdivision approximation. Of course, the closeness depends on how many layers of recursion have occurred, because each time the tolerance is being divided in 2 and separately allotted to each side of the interval. So if we summed up all the various 1 division minus 2 division differences, they would add to less than 0.0005. That's not to say that it's within 0.005 of the exact integral. It's a heuristic stopping criterion, as I mentioned. Let's make it even finer. Finer yet. Same density variation. 2 more. Same general trend is occurring. Now there's about 120 evaluations in this last third.